Hi everyone, we are back and we are about to zoom out a little bit and we are going to go ahead and run our lab, which is basically our first lab, our statics lab. So we're going to have two of our Vernier force plates. One of the important things is to just make sure you're on the lower end of the settings here so you can actually see a range. Ooh, let's see if we can focus on this. So basically, let me kind of set this up. Here we go. Focus. Well, you can see here, one range is basically up to 3,500 newtons. The other range is only up to plus 850, minus 200 newtons in compression. So we're going to go ahead and set those up on that lower end. So just make sure you flip that switch. I'm going to go ahead and set these up right now. And our two force plates, you want to have two of these 0.5 kilogram weights from Pascal with you as well. You're going to want your piece of wood right here, and you're going to want a ruler as well. So with that, let's go ahead and get started. So these are actually going to be hardwired in. We're going to work with some Bluetooth sensors in a bit. So you're just going to connect each of these to this little tablet. Is going to have 3 channels here. So if we can see channel 1, 2, 3, doesn't really matter which one you plug in, but we'll go ahead and plug that in right now. So let's go ahead. We're going to take this. We're going to plug in the first channel right here, and then you can see that we're plugged in here. So plug that one in there. We're going to go ahead and plug this in right here. So let's plug in. You can see I'm doing it with one hand. Here we go. So we've got our 2 channels plugged in, so now we can actually go and we're going to click on Home. And we're going to click on the LabQuest app, all this touchscreen. So you see already right now, we're getting a reading of 8 newtons, 5 newtons for these different ones. So we want to, before we put anything on here, we're just going to want to 0. So let's go ahead and 0, and then we're going to 0 here. We can calibrate if we wanted to do some measurements like that, but we are going to avoid doing so. So we're as close, again, you see some fluctuation because, again, these are pretty high force sensors. You can buy and purchase or actually develop your own force sensors that have much better sensitivity. But let's go ahead and run our first set of experiments. So we are going to put our, basically, piece of wood here. We're going to kind of drag it out a little bit. Right at the center. So you see kind of we have these 4... kind of screws here. We want to put it right at the center, and we're going to confirm, and we're going to try to be as nice and even as possible. So try to match these up, and we'll confirm with our ruler just basically the amount that we have on, actually, here we go, on the actual sensor itself. So right here we can see we've got about, basically almost 5.5 inches right there. So let's go ahead and look, actually, we'll go ahead and see. So 22, and then we've got a little bit too much here. So let's try to even these out. So this would be about 6 inches now. And I also want to avoid having too much torque there. So we got about 6 inches here, and then now we've got a little bit more than 6 inches here, but we're pretty close. So we can maybe just a little bit, but we're pretty straight now. So, and as you might expect, they're looking pretty even. So we've got 2 reaction forces we want to find for the weight. So we are going to capture this data, and then we're going to compare it in the next segment of this video. We're going to do our free body diagram and compare our real structure to what we measure so we can solve for the weight. But we're going to calculate, and we're going to actually gather data at basically 50 samples per second, for 10 seconds. So to do that, we just click on play. Press play here, and we're collecting. And it'll give us a close-up view in a bit. But you see, as you might expect, we're pretty much even there. So let's go ahead, and we're going to use this data to solve and actually calculate what our mass is. So I've got the flash drive here, so I'm actually going to go ahead and I am going to plug in my flash drive into this port right here. Oops. Let's go ahead. plug my flash drive right into this port. And we'll go ahead and save. So I can go ahead and say, I have some connection here. Okay. I don't need to. Let's just go out. So I'm going to say EXP1. Probably a better file name, but we can see this experiment 1. I'm going to click on done. And then I'm going to take my data. Let's go back to our graph. I'm going to file. I'm going to export that. And I'm actually going to title it here, EXP1. And we'll go ahead and click on done here. And export to text file. And we'll just make sure file export. Actually, let's go ahead and we're going to do file export here as well. And we'll export it. It should be the same. So let's go back here. So we have shown what we're going to do in the lab. We've actually gathered our first set of data. So let's go ahead and work on what we're doing in our lab. So the first thing that we want to do is in our first experiment, and we're going to go ahead and you can set up your submission, hopefully something like this. So experiment 1, we had a situation where we had our body and we have right at the center, we had a mass or weight. So our weight is equal to mg. We don't know what m is, but we know that when we place this on the beam, we're going to have a reaction 1 and a reaction 2, or normal 1 and normal 2. Let's go ahead and keep it in this notation. Normal 1, normal 2. And we can use our fundamental equations. Sum of the forces in the y must be equal to 0, our coordinate system, x, y, as always. Make sure we include this. So this is our free body diagram. Sum of the forces in the y must be equal to 0, which is equal to minus w plus n1 plus n2. And we knew that on our force plates that we were measuring, they're about 6 inches apart. So we know that they were basically at the edge of these beams here. So we can use this to solve for the weight. So to do that, we're going to go ahead and we're going to open up Excel. We could do this in Mathematica, and I'm very tempted to do so, but you'll do that a little bit later on in your first year students, so we don't need to kind of do that just. So we have to open our file. And actually, let's going to open it right here. Let's go ahead and open our file. We got to go to our USB drive. And then we need to click on all files because we're actually working with a text file here. And we can go ahead and click on experiment 1. And it's going to be, we have to format it a little bit, but it's already formatted automatically. So now we can take this data set. Actually, we'll go ahead and do, we're going to do insert, and we want to do a scatter plot. A scatter plot that's connected. We're going to select data. So we're going to add a data set. We're going to call this N1. We're going to select here. Here all the way down to 10 seconds. 508. Control this. Good. And then we're going to do the same thing here, except we're going to do this. We're just going to change this. Oops. Okay, it doesn't like it. B here, 8 to B 508. And that's N1. Don't you like? We need that little, basically before here. we need to put a semicolon. Whoops. There we go. So we've got our N1. Let's add another one, and we're going to do the same thing. We're going to go from here to, oops, let's call this, for example, let's call this N2, not N at, N2. We're going to go from here, A to 508, and we're going to go from here to 508. And we'll have 10 seconds. Great. We want to format the axis. Actually, we're going to want to add axes titles, and we want a legend. So we want this to be force in newtons, and include a picture of this in your report as well. Force in newtons. We're going to have this time in seconds. And you see we're pretty close. We're, they're overlapping a little bit, plus or minus a newton. To do our calculations, we're just going to roughly go ahead and say, all right, well, we're going to take actually the mean. So what we'll go ahead and do is we're going to go ahead and copy all this all the way to 508. We're going to calculate this. You're going to see soon in your classes, it's so much nicer when you can do this in programming, so you don't have to copy and paste these the whole time. We're going to do the average. The average should hopefully show up below here. That's our average. We can go ahead and drag and click this over here to see this average. So we see we're, basically plus or minus 1/8 of a newton, which is pretty well within our range of air, or bounds of air. So, but we will go ahead and use those values. So now we can use Mathematica, and we're going to calculate what the mass is. So I'm going to go ahead and clear everything. Quit our kernel. So we have weight equals mass times 9.8 gravity. Our normal 1 is equal to about 3.36. Our normal 2 is equal to 2.57. And we can now go ahead and solve, actually, our equation, f of y equals 0, which is equal to minus w plus n1 plus n2. And we can now solve fy, and we have our mass. Fantastic. So now we can go ahead and proceed with our second experiment. All right, so we are back to our next experiment. So what we're going to do now is we're going to actually place both of these Pasco weights on one side pretty close to the edge of the sensor here. And we're going to actually measure what's the distance from here to here. And we can actually see it's about, just getting roughly, we're about 2.5 inches here from the center of our weight to the edge of our force plate on the left side. So when we do that, we can actually record and measure what are the new reaction forces. So we know each of these are 0.5 kilograms. We can kind of basically back calculate it, but we'll convert and we'll actually ensure that our measurements are accurate. And you see now the reaction forces are different. And why are they different? Well, we have that weight now that's being additional weight in addition to the mass of the beam. And so now, let's go ahead and confirm, because we know some of these masses, let's confirm if our result is correct using some good statics analysis. And before we leave this video, I'm going to go ahead and export right now. And this is going to be my experiment 2. And now, let's go ahead and let's go and do our analysis on this data and some free body diagrams. So see you in the next video. So before we start our next analysis on our second experiment, let's just go ahead and we're going to grab this and we're going to put it in our document. Because remember, what do we need for our submission? And obviously, do as I say, not what I do. Make this a little bit nicer in your submission. So we want to measure the forces. We want to add the masses. So we want to calculate the weight, so we have our free body diagram, and we have graphs of the forces as well. So you're going to want to do this over and over. So for our experiment 2, however, we now have some changes. So now experiment 2, our free body diagram, and we still have our coordinate system, now looks like this. So we have reactant 1. Oh, I keep saying reactant. Normal 1, normal 2. We have right at the center of our beam, we're going to have here basically a length here. Let's go ahead and check that out quick here. So we have our total length of our beam, which you might have seen in the video, but we didn't, I don't know if we said explicitly, is going to be about 18 inches. So we need to take that measurement. And we put an additional mass here. And actually we can go ahead and we put an additional mass about 2.5 inches. Put an additional force here. We can just put it like this. And that is, those forces actually was 1 kilogram. So the weight of that will be, so basically another weight, so weight 2. So weight 2 is equal to, ostensibly, it's going to be 1 kilogram times 9.8. So we can actually figure out what should be the sum of the forces here. So this is going to be weight 1. And we solved for our weight previously. And actually, let's go ahead and write that down explicitly. Actually, we still have that in our Mathematica notebook. So for our mass. So for our mass 1. So we're going to actually call weight 1 equals this times 9.8. And weight 2 is going to be equal to 1 times 9.8, because that's kilograms. So now we can go ahead and say sum of the forces in y must be equal to 0, which must equal to minus weight 1 minus weight 2 plus normal 1 plus normal 2. And now we have to actually figure out and do some moments to solve for other unknown, because we have 2 unknowns in this problem. Again, ostensibly, we're going to double check with our experiment. So some of the moments about 1 right here. So what's my perpendicular distance? So it's going to be equal to 0. It's going to be equal to minus weight 2 times, and actually I'm going to zoom out here, 2.5 inches, but again, we don't want to deal with inches. We want to do to meters, so 2.5 inches times 0.0254 meters per inch, or actually, meters per inch. So these cancel. So we're going to have to include that in there. And then the distance from here to here, we can kind of just cut that in half. Actually, it's going to be 9 inches. So that's going to be minus W1 times 9 inches times 0.0254 inches per meter, or meter per inches, plus N2 times 18 inches times 0.0254 meters per inch. Cancel, cancel. So now we can use these equations to solve for the unknown and compare it with our actual experiments. So what can we do here? So let's go ahead and solve. Actually, not solve. Let's write out our equations. So, but first I'm actually going to quit everything. I'm going to quit the kernel, and we're going to restart. So we're going to go here. So we're going to say weight 1 is this, weight 2 is this, everything else is unknown. So we're going to say Fy equals 0, set it equal to minus W1 minus W2 plus N1 plus N2. We're going to say that our M1 equals 0, set it equal to minus W2 times 2.5 times 0.0254 minus W1 times 9 times 0.0254, and then plus N2 times 18 times 0.0254. Now we'll solve for both of those. Fy, M1. Normal is about 11. Normal here is about 4.32. Again, with our error, probably plus or minus a Newton would be great. So let's go ahead and check it out. Let's open our second experiment file. And we're going to go ahead and open experiment 2. All files. Let's go to experiment 2. Finish. Let's look at normal 1. Let's take an average. Let's do an average here. Let's go back down. Let's double check our results. Let's drag this one over here. Let's check it out. So about 6 and 9, what was our prediction? Again, this is our normal 1 in our instance, so it's a little bit backwards, but here and here, yeah, pretty close. Again, from very, very, very rough approximations in terms of where's the center of mass, where are those values, factoring that error, we're great. We're basically within our kind of error effectively, about plus or minus a Newton, Newton and a half. Excellent. Now, let's see the results from our next experiment when we flip those directions. So now for the final experiment, let's go, and now we can see and measure. So now we have that we're actually do it a little bit further away here. Let's measure it right here. So now we're about, well, we're almost about 4 inches from the edge of the beam here. So we'll go ahead, click on Run. And we can see some change here. And now we're going to export our data from our last experiment. Make sure, hopefully, that it matches our expectations, even though understanding it's going to be a little bit different, obviously, from the real experimental results. And that's it. So make sure to include these graphs. Make sure to include your free body diagrams and show your calculations. And you completed your statics lab. Congratulations. See you in the next lab. So remember, in your submissions, make sure to plot this as well. So now let's go to our last experiment. Our last experiment is going to look very similar to this free body diagram in the sense that we're still going to have this coordinate system here, x, y, positive here. We still have our beam with this length. We still have a normal 1. We still have a normal 2 here. We have a weight 1 here. And now we have that same weight 2 here, but now it's just shifted over here about 4 inches from that normal. And now we can go ahead and start to set this problem up and get ready to go. So let's make sure that we have those values. So our first equation holds true. Really, the only thing that would change here, if we keep this as our moment, we're going to have a minus W1. This still holds. The minus W2 now, though, would be from here to here. So that's 4 inches minus 18. So it's going to be, this value here would be 14 inches. And then N2 would be all the way over there. So really, that's the only thing that would change in our expression. So I'm actually going to go ahead and copy this. We still ostensibly have the same weights. I'm going to clear the kernel. And I'm going quick now because, again, this is kind of what you're going to do in the lab. So I don't want to take away too much fun. But this is our weight 1. This is our weight 2. And again, you want to pick your own distances and explore. So that's your kind of prerogative in the lab. But this is kind of how we want to do the analysis. Weight 2 will be 14 inches away now. Everything else remains the same. And you see that shift, right? So we should see that shift that occurs. And let's go ahead and look in our data and see if it does occur. Always make sure to, again, you should plot it. Again, that's required for the assignment. So make sure that that is indeed the case. So we should see a flip now in our N1 and N2s. So now we do indeed see now this one's larger. So this was our N2. I know it's a little bit poor notation from me just because we kind of flipped up our sensors. But again, you can make sure we can keep track of it. It's not too bad. It's not too complicated. So let's go ahead. We'll take an average here and then go down. Flip it over here. And let's see what this compares to our values. Look at that. I mean, pretty close. Very, very nice. So we got it. So it's important to really measure your distances correctly. I have a feeling that, for example, on this one here, if we're a little bit, which we could be about 3 inches, I think previously, we probably would have gotten a little bit closer. Actually about 2 inches. Oops. I think we were a little bit closer to the edge there. Oops. Actually, 3.5. I think we would have gotten a little bit closer. Yeah, actually, I think we're a little bit closer to our actual values that we measured. But you can see we're pretty close to this value. So this is fantastic. Again, there's always going to be fluctuations in our. We're using sensors that aren't as precise. So there's going to be some fluctuation, but this is pretty close. And you see kind of that drastic flip and the change in those normal forces when we add those additional masses and weights to our system. So fantastic. Congratulations. Make sure, again, we need to see a full free body diagram. I want to see all of the equations and a plot for each of your 3 experiments. But with that, have a great day. You finished your statics experiment, and we'll see you next time. Thanks. Bye. For some vibrations lab. Very, very fun, coming soon.